Our world relies on a stable power grid, right? I mean, completely.
Absolutely.
But what happens when we start adding massive amounts of new clean energy? Think solar, wind.
Yeah, it's exciting stuff, but it does bring challenges.
Exactly. Challenges for keeping that power flowing smoothly. So today we're doing a deep dive into protecting these crucial microgrids, especially when they use distributed energy resources, or DRs.
And our mission here is really to unpack some fascinating new research. We're going to look at a core problem, or a real dilemma, actually.
All right.
How do you keep these sometimes sensitive renewable sources stable when something goes wrong on the grid? Without just tripping everything offline.
Right, you want to keep things running.
It's all about ensuring your lights stay on, even as our whole energy landscape is transforming.
Okay, so to really get into this, let's talk microgrids.
Yeah.
They're becoming so important for a sustainable future.
Definitely.
But integrating DRs, again, things like solar or wind farms, well, it significantly changes how electrical faults behave on the grid.
Totally different signature sometimes.
Which makes traditional grid protection pretty challenging.
Yeah.
Now, directional overcurrent relays, DOCRs, they're key players here.
They are.
But here's the catch, and this seems important. DRs, unlike the big old traditional power plants.
Yeah, the big spinning generator.
Right. Those DRs have really low inertia.
And that low inertia is, well, it's central to the issue we're discussing.
Yeah.
It makes these DRs extremely susceptible to instability if a fault isn't cleared very, very quickly.
Okay, so speed is critical.
Super critical. And this creates a real challenge. See, relays need to coordinate properly with each other. They need to maintain what's called a coordination time interval, or CTI.
CTI, okay. How long is that usually?
Typically, maybe a 0.2 to 0.5 seconds. Enough time. So the closest relay tricks first, not the whole section.
Makes sense. Selective tripping.
But, and here's the dilemma, they also need to clear that fault before the DRs become unstable. That's within their critical clearing time, or CCT.
CCT. So you have CTI for coordination, CCT for stability.
Exactly. And the CCT for some DRs can be shorter than the required CTI. A single traditional relay characteristic often just can't satisfy both.
So you risk either messing up the coordination
or the DER tripping offline from instability.
Yeah.
It's like trying to thread two different needles at once.
Okay, this feels like where the new research comes in. You mentioned a solution.
Yes. So the paper we looked at proposes this really novel solution called the Shifted User-Defined DOCR. Let's call it SED-DOCR for short.
SED-DOCR.
Catchy.
Well, maybe. But what's clever is how it uses modern digital relays. Instead of just one operating curve.
It uses two.
Exactly. Two inverse operating curves. They call them a main curve and an auxiliary curve.
Okay, why two curves? How does that solve the CTI versus CCT problem?
Well, think of it like this. Maybe like having different driving modes in a car. The main curve is your standard drive mode.
Okay.
It's set up for that conventional relay coordination, respecting the CTI.
Right, the normal operating procedure. But the auxiliary curve, that's like your sport mode, or maybe even an emergency brake assist. It's specifically designed for rapid tripping really fast, only when there are high fault currents.
So it kicks in just for those dangerous faults that threaten the DRs.
Precisely. It ensures you meet that critical CCT for the DRs, protecting their stability, while the main curve handles the everyday coordination. It's dynamic.
That sounds much more flexible. So does it actually work? What did the evaluation show?
Oh yeah, the results are quite compelling. They tested it on a modified IE33 bus system, a standard benchmark.
Yeah.
So get this. A conventional relay might take, say, 300 milliseconds to clear a certain fault. But if the DRR CCT is only 200 milliseconds...
Oh, instability.
You got it. Instability happens.
Yeah.
But this proposed SUD-DOCR, it clears that same fault in just 180 milliseconds.
Under the wire. It
Yeah.
keeps the DR stable.
Exactly. Overall, the method/relay operating times by about 82% for the faults near the relay and around 69% for faults further away, compared to using just a single curve setting.
82%. That's a massive improvement.
It really is significant. It shows this approach can make a real difference in grid reliability with high DER penetration.
And is it just a one-trick pony, or can it adapt? Like, what if grid conditions change?
That's another strength. It's flexible. For example, if you have a situation like a 10% load reduction, the CCTs for the DERs actually tend to increase. They get a bit longer.
Okay.
So the system adapts. The main curve can then handle a wider range of faults while still maintaining coordination.
So it adjusts its strategy based on conditions?
Yeah.
What about things like false trips? Sometimes you get high currents that aren't faults. like transformer inrush?
Good question. Yeah, transformer inrush currents can be high, but they're very brief, typically like 0.1 seconds. The study showed the SUD-DOCR is immune to this.
How so?
Its operating times for those kinds of currents are much longer, in the range of 0.46 to over 2 seconds, way longer than the inrush duration.
So it correctly identifies it's not a sustained fault and doesn't trip.
Exactly. No false trips from that. Which, really raises a broader point. As our grids get more complex, more packed with renewables.
Yeah.
How will these ongoing innovations and protection schemes like this SUD-DOCR continue to shape the resilience, the robustness of our entire energy future? It's something to watch.
Absolutely. This deep dive really shows how cutting-edge digital relay technology is stepping up. It's fundamentally changing grid protection to make sure our modern energy sources stay stable and, reliable.
It's pretty amazing stuff. So maybe the next time you flip a switch, think about it. Consider the intricate, split-second decisions and these really ingenious solutions working constantly behind the scenes.
Right. All happening to keep the power flowing reliably and keeping our increasingly dynamic energy landscape secure.
Couldn't have said it better myself.